In Chapter 4, we're going to be discussing maxima and minima. You can think of maxima and minima as above and below. The maximum being the point that is above all the others, the minimum being the point that is below all the others. We have this definition of absolute maximum and minimum. First off, f has to be defined on an interval, and it has to contain whatever point C. If that f of C is above all the other points, then f has an absolute maximum. So if at this point it is above all the others, then it's called an absolute maximum. If, however, f of C is below all the others, or is less than, then he's an absolute minimum. So let's look at a few different cases so we can see if we have absolute maximum minimums. In this first case, we're looking at the interval where this function goes on and on in both directions. There is no point on this function that is above all the other ones because the function keeps on going up and up. So we say that this function has no absolute max. So no absolute max. The function, however, does have a point down here at the bottom that is below all the other ones. So we say that it has an absolute, and this is real picky here, absolute min of 0 occurring at x equal 0. The minimum or the maximum is actually the y value, and the and where it happens would be the x value. This is going to be real picky, especially when you're answering these multiple choice questions. So note that the min or max is the y value. So y value is the min or max, and x value is where this happens. Let's look at the rest of them. This happens to be a closed interval, so it has endpoints here and here, and they are included. Notice that they have to be included. We're not talking about any point that goes up to but not including. That's going to be very picky here in just a minute. So we have an absolute max of 4 occurring at x equal 2. So there's my absolute max of 4 occurring at x equal 2, and that's what they've stated right here. This next one is an absolute min of 0 occurring at x equals 0. Note how they're very specific in their language. This one I have an open-ended on the left, meaning that that point 0, 0 is not included, which means there is no absolute minimum. Notice that point has to be included in the function for it to have an absolute max or min. That absolute min, there is none, because it just keeps getting closer and closer. There's no one point that is the absolute minimum. But likewise, we still have a closed interval up here, so that's the same as before. If I have an open interval, I don't have a maximum or a minimum, absolute maximum or a minimum on this particular function, but I could. Let's say I had a function that looked like this, and it was open-ended on both. I still could have an absolute maximum right there. So just because it is an open interval doesn't mean that you don't have an absolute max or min, so don't get that idea. This next one, here I have a total closed interval. All points are included, but it's not continuous. I do have absolute mins, and they are minimums of the function, and they occur at x equals 0 and x equal 1. However, I don't have an absolute maximum because that point is not included It just keeps getting closer and closer up there, but it never quite reaches it. In this next case, I have an absolute minimum and I have no absolute maximum because that is an open-ended point. But notice I still have a closed interval. It's just not continuous. That's the point on this one. In looking at this extreme value theorem, note it says a function is continuous on a closed interval. So if I have a function that is continuous on a closed interval, then we know that we have an absolute max and an absolute min on that interval. But it must be continuous on that closed interval. So let's look at this first example, and we're going to identify I have at x equals c, I have an absolute min for this a. Let's see, it looks like I have an absolute max. I have an absolute max. Oops. And these points, they don't concern me because they're not absolute maxes or min. Does it meet the criteria? Yes, because it is continuous on a closed interval. Therefore, I knew I had an absolute max and an absolute min. This next one is not continuous, nor is it a closed interval. That lets me know that I don't have to have, I can have an absolute max or min, but I don't have to. In this case, it looks like I have at x, let's say this is b, x equals c, I have an absolute max. And I have no absolute min. So to answer the question about does it meet the conditions of the extreme value theorem, just to emphasize, the A graph does meet those conditions because it is continuous on a closed interval. The B graph does not meet it at all. It's neither continuous, i.e. that right there, and it's open-ended. A and B aren't included in that. They're both exclusive. Next up, we're going to define local maximum and minimum. So let's look at the definition. We have an interval. F is defined and C is some interior point of, notice that C is some interior point of I. That means can't be an endpoint, doesn't it? If that f of c, or if those y values at c are greater than all the other y values in some open interval, meaning some neighborhood containing c, and I know we've discussed neighborhood when we were discussing limits. Let's look at this neighborhood. Notice how the y values at this point D are all above my D, so my D is at a minimum. Let's write down our list here. Alright, we said that D was a local min, so x equal D, we have a local min because he is below all those points around him. He is not the absolute min. The absolute min occurs at x equal A. But notice there's no real neighborhood, there's not an open interval around this A so that I could say he's local. He's an endpoint. This value here would be a local max. It is not the absolute max. So x equals c is a local max because he is greater than all those points around him. At x equal e, I have a local max and I have an absolute max because he's greater than all those other points on the function, greater than all those y value points. And at b, I don't really have anything because he's not a local, can't be, and he's definitely not an absolute. Let's look at example 2, and we'll just make our same list again. Alright, look at some of these points. I see that right there at P, I have a local min, x equal P. I have a local min. It's also the absolute min, isn't it? X equal P. At R, I have another local min. At x equal Q, I have a local max. And it looks to me like Q and S are both the same height. So I'm going to say that Q and S are both absolutes, and of course they're also both locals because they're those interior points. And at A and B, I don't have absolute extrema there. In this next little bit, we're interested in defining critical points so that we can find local extrema. A critical point is a place at which the derivative is 0 or it fails to exist. Those two statements are the criteria. You can have either one of those and it will be a critical point. On this local extreme point theorem, if f has a local max or a min at C and the derivative exists, then we know that the derivative equals 0. Now they gave two cases here where it kind of violates that local extreme point theorem, or two cases where it doesn't really apply. So if we look at this case, we have a local min at C, but the derivative does not exist. So the local extreme point theorem would not apply because I would have to have both these two cases in order for the local extreme point theorem to operate. In this particular case, because of that corner, the derivative doesn't exist there as well, so the local extreme point theorem would not apply in this case either. We also note a couple of cases where this critical point definition doesn't go backwards, is what they're trying to show you on this. So for a critical point, the derivative must equal 0 or it fails to exist. Notice that the derivative equals 0, but it doesn't mean that I have a local max or a min. Here the derivative doesn't exist, but it doesn't mean that I have a local max or min. So what this says is just because you have a critical point doesn't mean you have a local maximum or min. But we know that local max and mins occur at critical points. But just because it's a critical point doesn't mean that you have a max or min there. We just know that they happen to occur there, so we go and find them. Now the graph is always something that I like to look at before I go and try to find critical points. I try to see, okay, what should my answers be? Now this wasn't the case years ago before a graphing calculator. You did the calculus and then you actually drew your graph from your calculus, but you guys get to work it the other way around. So I'm going to take the derivative because I know critical points happen where the derivative is either 0 or fails to exist. So let's see what I get. I'm going to need to use the product rule here, so I'll take the derivative of the first, leave the second one alone, add to that. This is going to be 2x, and then, oops, sorry about that. Alright, oops, I still have my eraser. Alright, So I already took the derivative of the first, so I leave the first one alone. Take the derivative of the second, which is just 1 over x. And this is going to be 2x natural log of x. Simplifying that, it's just going to be an x. I'm going to factor x, and I will have 2 natural log of x plus 1. I need to see where this derivative fails to exist or equals 0. I don't see a place where it's going to fail to exist, but I can see that it is going to equal 0 at either x equals 0 or 2 natural log of x plus 1 equals 0. So natural log of x equals negative 1/2. E both sides. And then I'll get x equals e to the negative 1/2, or 1 over the square root of e. Now my x equals 0 point has to be, it can't work because it has to be an interior point for it to be a critical point. So that x equals 0 isn't an interior point, so that's actually not a critical point, but x equals 1 over square root of e is a critical point. And that was all they asked me to do. So they gave me the graph just so that I could look at it. Note that the derivative equals 0 here, which means the slope of the tangent line is a horizontal line. That's why it's going to be a local minimum, because it is a place where the derivative actually went from going down, or a negative slope, to going up, and that will become important later on. Alright, let's play. I'm supposed to find the absolute, maximum, and minimum values for these functions. I know that I can have them on endpoints, or I can have them on the interior. So I need the derivative for x cubed minus 6x squared. Next thing I'm going to need to do is solve this for 0. There's no place where it's going to fail to exist, so I'll ignore that. I'm just going to go ahead and pull out a 2x squared, and then I'll get 2x left there minus 3. That will give me x equals 0, or x equal 3 divided 3/2 for being critical points. So I've located the critical points where the derivative is 0. The next thing I'm supposed to do is evaluate f at the critical points and at the endpoints. So I chunk in some numbers. So x equals 0, x equal 3/2, x equal, my interval is x equal negative 2, x equal positive 2. And then I'm going to go get the y values for each of these. Just going back to your original function and just plugging in those x's. For x equals 0, you're going to get y is 0. For 3/2, chunking that in, you're going to get negative 27 over 16. At negative 2, you're going to get 32 when you crunch those numbers. And at 2, we will get, that's where we get a 0. Absolute biggest, this one. Absolute max. Absolute smallest. Right there. Absolute min. Let me go ahead and state that these are the two critical points. Let's play with the next one. I'll need g prime of x. This I'll use the product rule. 2/3 x to the minus 1 and be minus 1/3. Lovely. Took the derivative of the first, leave the second one alone. Great, didn't leave myself enough room. plus x to the 2/3, and the derivative of that would just be -1. I need to clean this up. This is going to be 2 times 2 minus x all over 3 onto the cubed root, great, of x plus, we'll just say cubed root of x squared. Oh, and it will be a minus. Let me fix that. Alright, I'm going to need a common denominator. Looks like it's going to be, yep, you guessed it, 3 cubed root x. Lovely. Okay, equals, I'm just going to leave this skinny pen, I like it better, 3 cubed root x. This is going to be 4 minus 2x minus, that combines into be 3 times, and that's just going to be a plain x, because x squared times x is cube root, x cubed, take the cube root, is just plain x. It's going to be 4 minus 5x all over 3 onto the cubed root of x, and I need to see where this thing equals 0 or fails to exist. I can see that it fails to exist at x equals 0 is critical point, because that'll be where it fails to exist, and that is an interior point of my interval. X equals, moving that over 4/5 is critical point. Next thing you're going to need to do is you list off all your x points, and then you're going to crank out the y values for those, including you get your critical points and you get your endpoints, and my endpoint here is x equal -1 and x equal 2. And then you get your y values for those just by crunching it into this equation. Okay, I have 2 absolute mins. Here they are. Absolute min, absolute min. I have 1 absolute max. Here he is. Absolute max. I drew the graph for you here on my calculator. Of course, these numbers over here don't make any sense because anything before the 0 time doesn't make any sense. I'm going to find what the maximum value is here. So I'm going to take the derivative, and that's going to be -32t plus 64. I'm going to set it equal to 0, and I know that maximums and minimums occur at critical points. So if this has a maximum, it's going to be at t equal 2, and it is, as you can see with the graph here. Alright, that's it for 4.1. See me in the Collaborate or email me if you have any questions.